Okay, so we're going to talk today about states of matter. We're going to begin chapter 12 with that. Objectives for this section. This is 12.1. You're going to have this in two sections. So these objectives are for the whole thing, not just today's. Use the kinetic. Okay, our objectives for this section: use the kinetic molecular theory to explain the behaviors of gases, describe how mass affects the rate of diffusion and effusion, explain how gas pressure is measured and calculate the partial pressure of a gas. The vocabulary we're going to review is kinetic energy. This is energy due to motion. New vocabulary, there's quite a bit of this. Tomorrow in class, you will see all of this listed. There'll be a PowerPoint up on the screen, and all of this will be listed, and you'll need to start working on this vocabulary in class. You'll watch a video, you'll do the vocab, and there are some questions that you'll need to do. Okay, so you can copy it down now, or you can wait until class tomorrow. Either way is fine. The main idea for this section is that gases expand, diffuse, exert pressure, and it can be compressed because they are in a low density state consisting of tiny, constantly moving particles. Okay? All right, the kinetic molecular theory. Kinetic molecular theory explains the different properties of solids, liquids, and gases. And so for right now, we're going to start talking about gases. Next, we'll move into solids later in the week, and then next week when I get back, we'll talk about solids together. The atomic composition affects chemical properties, so which atoms with which elements make things up, obviously are going to change what the chemical property is. Atomic composition also affects physical properties. So it's not just going to affect chemically how it's going to react, but it's also going to affect physical properties. Things like chlorine. We know that chlorine on its own has to be a diatomic, and it has to be a gas. Okay? Bromine left on its own is going to be a liquid. Okay, these are just the way that different atoms are put together will determine their chemical and their physical property. The kinetic molecular theory describes the behavior of matter in terms of particles in motion. That's why you have the whole kinetic part here. And gases consist of small particles separated by empty spaces. This is what separates gases from liquids or solids, is that you have the empty space in between. Gas particles are too far apart to experience significant attractive or repulsive forces. This is an important thing to remember. Because you have this empty space in between, the gas particles themselves do not have any attraction or repulsion. They're not pulled together or pulled apart from each other. Okay? They will bounce off of things and cause friction and energy that way, but they themselves are not pulled together or pushed apart because of that space. Gas particles are constantly in random motion. So just looking here, you see that when you start to compress, when you have gas in a cylinder and you begin to compress it, you start to see motion. An elastic collision is one in which no kinetic energy is lost. So that means that all the energy stays. Kinetic energy of a particle depends on mass and velocity. Temperature is a measure of the average kinetic energy of the particles in a sample of matter. So we have this formula here. Ke, kinetic energy, is equal to 1/2 of mass times volume squared. Great amounts of space exist between gas particles, like we already said, and compression reduces the empty spaces between the particles. So if you start over here, okay, where we have the most space, all right, they will collide with each other, but not nearly as much as they will here where they're all compressed. Gases easily flow past each other because there are no significant forces of attraction. So when gas particles, they might collide, but they're not going to be attracted to each other. It's just random as they're constantly moving. Because remember, gas particles are constantly moving around. Diffusion is the movement of one material through another. So diffusion is how, let's say they move out. You have a porous substance, and so the gas is able to leak out through that. That is diffusion. Effusion, on the other hand, is gas escaping from one tiny point. Okay, so if you have a gas tank and you puncture a small hole in it and all the gas is coming out from that one spot, that's effusion. Okay, if you have gas in a container and you take the lid off of it and it's able to escape through a large opening, that's diffusion. All right, Graham's law of effusion states that the rate of effusion for a gas is inversely proportional to the square root of its molar mass. Okay, so the rate of effusion is equal to 1 over the square root of the molar mass. Graham's law also applies to diffusion. So here, if we find out the rate of effusion of A and B, those are applied to the molar mass, the square root of the molar mass of those. Okay, but they're going to be inverse in this formula. Okay. So ammonia, we're going to get to some problems here and explain using these two formulas. So rate of effusion is 1 over the square root of the molar mass, and then comparing rates using the square root of the molar mass inversely from the rates. Okay, so here's your problem. Ammonia has a molar mass of 17.0 grams per mole. Hydrogen chloride has a molar mass of 36.5 grams per mole. What is the ratio of their diffusion rates? So we start off with the rate of ammonia over the rate of hydrogen chloride. We'll take then the square root of 36.5 grams is the molar mass of hydrogen chloride, and 17.0 grams per mole is the molar mass of of ammonia. Okay, so if you divide that, take the square root, you end up with 1.47 as your answer. Okay, so this is the end for today. Tomorrow you'll be watching a video on this idea and then doing some problems. So have a good evening.